Yeah, I'll start with a brief reminder of what we've seen yesterday, and then we proceed to today's topic, since we actually also started yesterday. Okay, so we saw what I called the fundamental theorem of Boolean function analysis, according to which, if you take any real valued function on the Boolean cube, notice we call the Boolean cube or sometimes called the hypercube, then it can be written down as a linear combination of the Fourier characters, or sometimes called Fourier basis functions. And the coefficients are called the Fourier coefficients. This entire thing is called the Fourier expansion. And we'll also see some other terminology today. And these Fourier basis functions, they're just products of inputs. So it's fairly simple. And just to remind you, the reason that this was correct was because these functions, they form an orthonormal basis with respect to the inner product. This one, which is the expectation of the product of the two functions, where the expectation is taken with respect to the uniform distribution for now. Okay, if we change this distribution, we have to change the basis also. Okay, so some basic properties. So this is just Parseval identity stated for one function. So if you sum all the squares of the Fourier coefficients, then you got the expectation of the function squared. And another useful fact is that if you look at the empty Fourier coefficient, so the Fourier coefficient corresponding to the empty set, then you get the expectation of the function. Okay, and this is, I guess, a special case of a general phenomenon. Is this formula for the characters. Okay, so this was a very brief recap, so hopefully now we're all on the same page. Yesterday we also saw linearity testing, but for now we can, yes, not only for now, we can just forget about it. Okay, so now we're going to move to a completely different topic, which is going to introduce one more character into the mix, which is influences. I'm going to define shortly. Okay, so the first paper in this area is due to Khan, Kalai, and Ninial. So yesterday I couldn't remember Jeff Kahn's name, so it's Jeff Kahn. And their motivation was this social choice question that I asked yesterday. So there's a choice between two candidates, and like I don't know how it is in Korea, so yeah, I don't want to make some mistake in politics. But let's say let's take some other country, like India, and one president is like Pakistan more, and the other one likes Pakistan less. Okay, so if more people like Pakistan, then we want the outcome to be more Pakistan-like. Okay, so we want this function to be monotone, in other words. Okay, but in elections, there are many parties who would like to control the outcome, and they're willing to bribe some of the voters. And otherwise, the voters vote randomly. Okay, if you look at actual elections, then this is actually not such a bad assumption. Yeah, it's usually roughly 50-50. And the question is, how many voters do you need to bribe? Okay, so if you take majority vote, which is more or less what happens in my country, then it's enough to bribe roughly square root n of the voters in order to increase the probability of your candidate by a constant amount. Okay? In other countries, for example, the US, the system is different. And as we will see today, maybe there are actually some advantages. Okay, so for this question, it's called the influence of coalitions. We don't actually know the right answer, so there's some difference between the upper bounds. So instead, what we will discuss is about influences. Okay? So it's about how much each voter influences the outcome of the elections. Okay, so this is a definition from social choice theory. Definition that f be a Boolean function. It doesn't have to be Boolean, but the definition we will give only makes sense for Boolean functions. So the influence of coordinate I is denoted by inf I of f. And this is the probability, if you choose x at random, that f of x is different from f of x when you flip the ith coordinate. Okay, so this means that we flip the ith coordinate. Okay, so I choose the rest of the votes randomly, and in another way of stating it is this is also the probability that f of x, where I change I to 0, is different from f of x when I change I to 1. Okay, so we choose all the remaining coordinates. And then I want to know whether, on average, coordinate I has an influence on the outcome.
That should be -1.
Right, thanks. There's a third formulation which instead of flipping I, then we resample I, and then we have to divide by, multiply by 2. Okay, so there are also other formulations, but this will be enough for us for now. Okay, so maybe see some examples to see that we understand the definition. So let's start with the parity function. Oops. So if you switch back to 0, 1, then it will be just the XOR of all the coordinates, which is the parity function. So what's the influence of coordinate I for any I for the parity function? What's the probability that coordinate I influences the outcome?
1.
1. Okay, now look at the dictator, x1. So x1 decides the vote. That's why it's called the dictator. So what's the influence of coordinate I? Okay, so it's 1 if I'm coordinate 1, if I is 1, and 0 otherwise. Okay, now for something more exciting. What's the influence of coordinate I for the majority function? And let's assume that n is odd so that it's well defined.
What is the majority?
So majority function, we take a majority vote over all inputs.
And choose and over.
Right, so n minus 1, choose n minus 1 over 2, over 2 to the n minus 1. Okay, so I'm assuming that n is odd. So coordinate I only has influence if the rest of the coordinates are exactly balanced. Okay, and then this is roughly 1 over square root f. Okay, and now I can state the checkout here. Okay, so every f from plus minus 1 to the n to plus minus 1 has a coordinate with influence omega of log n over n times the variance of n. Okay, so for example, if f is balanced and the variance of f is 1, and then it's just log n over n. Okay, and now the variance, it has to show up here because if I take, let's say, a constant function, then no coordinate will have any influence. Okay, so it's important that the variance appeared here. Now you can see that for majority, we don't get log n over n, we get 1 over square root n, which is a lot larger. And you can ask whether you can get log n over n, and we'll see it shortly. But first, I want to explain how this relates to what I asked you yesterday. Okay, so there are two interpretations of this definition of influence. So let's first say that the function f is monotone. Okay, so if I fix the value of coordinate r to 1, then I increase the expectation of the function by the influence, or half the influence. I guess by the influence. Yeah. So if I set the coordinate to 1, then I increase the influence, the expectation of the function by its influence. It follows from the definition. Okay, so the influence is the probability that this makes a difference, and then I just increase the expectation. Okay, so let's say that my voting function is a monotone, and I want it to be biased towards 1, probability of 80%. So I want the expectation to be whatever, 0.7 or whatever. Okay, so what I do, I constantly pick a coordinate with the maximal influence. And as long as the expectation of the function is below 0.7, then I can always increase the expectation by at least log n over n times some constant. Okay, this is because as long as my function is not biased, then the variance won't be too small. Okay, and after like n over log n iterations, roughly, then the explanation will have to pass this 0.7. Okay, so it's enough to bribe n over log n voters. Okay, so this is one interpretation of influence, and in this interpretation, I don't have to look at the votes. If the function is not monotone, then the interpretation is that if I look at the votes, then I can fix coordinate I to my favor in case it's influential. Okay, so it's exactly the same argument, but now instead of bribing the voters ahead of time, then I somehow get access to all your votes, and then just bribe some of you to change your vote. Okay, so this is what I have to do if the function is not monotone. So this is the difference between voting and this collective coin flipping. Okay, so if you didn't follow, it's not a big deal. Just intuitively, this log n over n, it translates to bribing n over log n. And there are some details, but let's not worry about them too much. Okay, so questions about that? Okay. So the next thing we're going to do is we're going to ask, is this log n over n tight? Is there actually a function, let's say a balanced function, where all of the influences are only log n over n? Okay, so I think it's probably appeared already in the paper of KKL. This function exists. And it's called the tribes function, and it's a good function to test your hypothesis, your conjecture in Boolean function analysis on. But it's kind of extreme. So the tribes function that looks like this. This is an OR. Okay, this is n over m. This is an and. M. And all of these are the inputs. Or if you want to write it explicitly, this is OR of I between 1 to n over m, and j between 1 to m of x ij. Okay, and we're going to figure out the parameters in a bit. Okay, so this is a read once, I guess, DNF. Now, why is it called tribes? So we think of each of these guys as a tribe. And the answer is, so now I'm thinking in logical terms. So it's 0, 1. The answer is 1 if there's a tribe where all of the tribe votes 1. And otherwise it's 0. So that's why they call it tribes. I guess from a social choice perspective, this is the whatever came to their mind. Okay, but in TCS we just call this a read once DNF. Okay, so what is the probability that this function is equal to 1 or that they're equal to 0? Yeah, so we momentarily switch back to 0, 1. So in order for this function to be 0, then we need all of the tribes to vote 0. Now for a single tribe to vote 0, the probability is 1 minus 2 to the minus m. And this is raised to the power n over m. Okay, so this is the probability. I guess 2 to the minus m is the probability that one of the tribes votes 1. So 1 minus this is the probability that the tribe doesn't vote 1. And if none of the tribes votes 1, then the answer is 0. And this thing is roughly e to the n over m 2 to the m. Nice. Okay, so 1 minus x for small x is roughly e to the minus x. Okay, so these are some calculations, so we'll try to do them not too somewhat briefly because they're impossible to follow anyway and they're not so important. But now, in order for this to be balanced, we need this thing to be roughly, let's say 1, I mean, maybe some other constant, but it won't make a big difference. So we need n to be roughly equal to m 2 to the m. So m is roughly equal to log 2 to the m, I think, minus log 2 to the m. Guys, sorry, n. So this is the size of each of the tribes. And the number of tribes is something like n over log n. Okay, it's some calculation, it's not so important. And now let's calculate the influence of one of the variables. Okay, so I want to know the influence of this guy. So in order for this guy to be influential, what we need is that the rest of the tribes, they definitely vote 0. Okay, and we need that the other guys in the same tribe, they vote 1. So the influence I, j, and they're all the same. So this is 1 minus 2 to the minus m to the n over m minus 1. Okay, so this is the probability is that all the other tribes, they do not vote 1, times 2 to the 1 minus m. So this is the probability that the rest of the tribe that does vote 1. Now, this thing, we know what it is. It's roughly some kind of constant. Okay, so all of this thing is roughly 2 to the minus m. Yeah, because so without the minus 1, it's we said it's not constant, and this minus 1 doesn't make a big difference. But what's 2 to the minus m? So you can see it's roughly m over n, which is roughly log n over m. Yeah, this is just a calculation from how we define m. Okay, so I personally don't like calculations, so there won't be too many of these, although they're unavoidable, but here really you need to see the calculation, and it just works out. Okay, so if you choose the optimal parameters, then this is what you get. Okay, so here for this function, all of the influences are roughly log n over n, whereas the variance is constant. And this shows that this expression is tight, at least for constant variance. Okay, questions?
Is this function unique schema construction of such f?
Yeah, so
Combination of
I doubt it. So generally speaking, in Boolean function analysis, we don't care about constants. Okay, so you see there's big omega and big O. I guess there's no reason to assume that this is the case. There are other questions regarding degree, which we'll see in a moment, where also the exact answer isn't known. But this kind of thing definitely comes up. Sometimes you can say something like this function is approximately optimal. So there is this result that we will not cover called majority is stablest. And then there's this other result which is called majority is not stablest. Okay, so how can both things be true at the same time? So forget about what stablest is, but majority is asymptotically stablest, but not strictly stablest. Okay, so if you want to know the exact extremizer, then usually we don't know. I mean, sometimes we do, but usually we don't know. But we can say this is asymptotically the best thing, and in that case, then it's kind of too much to hope for to see the extremal cases. Yeah, so I don't think the extremal cases are known. Yeah, but it's a reasonable question to ask. So. Yeah, as you will see in the proof of the KKL theorem, there's, I mean, you won't really see it, but there is a lot of freedom. So you can, if you want to optimize the constant here, then you can do it, but I think nobody bothers. But it seems to me plausible that you would be able to at least find the optimal constant. Yeah, but this still won't be enough to find the optimal function. Yeah. Right, a good question. Yeah, other question. Okay. So what we're going to do now is we're going to discuss the proof of the KKL theorem, which hopefully will be done by tomorrow. Okay, you can, if you want, we can do it like a marathon quickly, but we'll do it somewhat slowly. So if you look at the early papers in this area, like the KKL paper, the FPN paper, whatever that is, they're all pretty short, but you can't see what's going on. And there's some demystification that will be helpful. So I'm not sure I will be able to do it, but at least I'll try a bit. Okay. So the first thing that we're going to do is we're going to find some relevant Fourier formulas. Okay, starting with the variance, because that's maybe something I should have done yesterday. So the variance of f, this is the expectation of f squared minus the expectation of f squared, is the sum over all s of f hat of s squared minus f hat empty set squared is sum over all s other than empty set of f hat s squared. Okay, so this is an example of a Fourier formula for something. In this case, for the variance. Okay, and it turns out that many of these concepts that come up, we have these nice Fourier formulas, and this is not by chance. It's because of the way that we define the Fourier basis as a kind of a product of a basis for one coordinate. Yeah, this is just a simple example. And we also, if we actually want to prove the Shakedown theorem in all generality, then we also need to know this, but we will only prove it in the case that the function is balanced, because it's a little bit simpler. Okay, so the next thing is I want to find the Fourier formula for the influence. And for this, we will need to, well, the Fourier formula will make sense for arbitrary real-valued functions. Okay, so we will need to somehow change the definition to something equivalent. Okay, so we define the ith Laplacian or the ith derivative at the point x. This is f of x minus f of x I over 2. Now, if f is Boolean, then Li f of x is equal to 1 if, I guess, squared. 1 if f of x is different from x I, and 0 if they're equal. Okay, so let's check this. So if they're equal, then of course you get 0. And otherwise, it's 1 minus 1 over 2, or minus 1 minus 1 over 2. So it's plus minus 1, you square it, you get 1. Okay, and this implies that for Boolean f, then the influence of I is the same as the L2 norm of LIF squared, which is the same thing as the expectation of LIF squared. Okay, and this definition makes sense for arbitrary functions. Okay, it coincides with the earlier definition when f is Boolean, but it makes sense for arbitrary function. And it will also allow us to give this nice Fourier formula. Okay, so I have to erase this, but this is not so important. Now, why did I choose this definition? Because if I apply Parseval to this thing, then I will get a Fourier formula in terms of the Fourier expansion of LIF. So if I can relate the Fourier expansion of LIF to that of f, then I will get a Fourier formula for the ith influence. Okay, so this is the idea here. Okay, so let's see what's LIF like. So this is, well, Li of this entire thing. And you can see that this operator is linear. Okay, so I can just bring this thing inside. And I just need to calculate this ith Laplacian of the Fourier characters. Okay, now there are two cases. So I want to know what is LIPS. So if I is not in S, then what can you say about this LIPS?
Zero.
Zero, right? Because if I flip the I coordinate, it has absolutely no influence. Okay, so in this case, LIPS is 0. Okay, what if I is equal to S? Then LIPS of X. So this is product of I and S xi minus product I and S of xi. And maybe I is not a good choice. Over 2. So this is because I is part of S, so this gets negated. And so flipping the I coordinate corresponds to negating it in the plus minus 1 world. Okay, so this is twice this thing over 2. This is just S. Okay, so if I is not in S, then this operator kills the character, and otherwise it doesn't change it. Okay, and as a consequence, we have this nice formula. We just have to square the Fourier coefficients containing I. Okay, so now this is quite nice, and it was also not so easy to see. Okay, so now we're already making progress. We're able to relate this influence to the Fourier extension. And the next thing we're going to need is what's known as the total influence. So it's another definition. The total influence of a function f is just the sum of all the influences. This might be the same as one of these indices in social choice theory. I never remember. Okay, so this total influence, after normalization, it's just if your function f is Boolean and you think of it as a partition of the cube into 2 parts, then after normalization, this measures the number of edges between the 2 parts. So the ith Laplacian, it measures the edges in direction I. And if you sum over all directions, then you get all the edges. Okay, so you're all doing external combinatorics, so you like edge isoperimetric inequalities. So this is the edge isoperimetric function. We call it total influence, but otherwise it's the same thing. Okay, there's a way to write it using the Laplacian, which is the sum of all the LIs. Okay, so if you know what that is, if you encountered the Laplacian when you studied Markov chains, and this is the same thing, but there's some normalization issues that just get it wrong, so I'm not writing it. But this is the reason for this notation with L. So this Li is the decomposition of the usual Laplacian, which is just the sum of the Li's. Okay, so this is the total influence, and it has a nice formula in terms of the Fourier extension. Okay, so this is the sum over all I, the sum over all S containing I of f hat s squared. Okay, so if I'm giving you a set S, how many times is it summed in, does it appear in this sum? Right, the sum of S. So sum over all S, S, f hat of S squared. Okay, so this is this formula for the edge isoperimetric, whatever, for the edge, number of edges cut by this function. Okay, now let's consider f's which are Boolean. Okay, so suppose f is Boolean. Boolean means it's for now, in this case, it's plus minus one valued. Then sum of s f hat s squared is one. So it's extension of f squared, which is one. So we can think of f hat s squared as specifying probability distribution over subsets of n, right? Because f hat s squared is non-negative and they sum to one. Okay, and in these terms, this is like the expectation of the size of S with respect to this definition, this distribution. Okay, so what this roughly means is that if your function has high influence, then a lot of its Fourier mass sits on high degrees. So the degree corresponds to the size of S. Okay, as an example, the function which maximizes the total influence is the parity function. And all of its Fourier mass is at degree n, because it's just the character of degree n. And if you take something like majority, then it's a bit different. Okay, and now we're ready to start the proof of the KKL theorem. But first, are there any questions? Okay, so far we've just done some calculations. So let's erase this. So we're proving the KKL theorem under the assumption that the function is balanced. And this really doesn't make too much difference. It just slightly simplifies the expressions. You can take it as an exercise to generalize it to the full case. So this is proof of the KKL theorem when a function is balanced, or equivalently, the variance is one. Okay, so we want to show that one of the variables has influence omega of log n over n. Okay, and we consider two cases. One case is when the total influence is large, it's like log n over a million. Okay, if the total influence is large, log n over a million, then the average coordinate has influence log n over n. Okay, so case one. Influence of f is at least c log n, where c is a suitable constant. Okay, which you can optimize and then get some better parameters, but I've never seen it done. So we really don't care about constants usually. Okay, so in this case, then there exists an I such that influence of I is at least c log n over n. Okay, just because, well, the total influence is the sum of influences. So if you take the maximal influence, then it will be at least c log n over n. Okay, so this was the easy case. There was nothing to do. Okay, case two, the interesting case. So the influence of f is at most c log n. Okay, now we recall that the expectation of this s is influence of f. And so the probability that this s is more than twice the influence of f is at most a half. Okay, this is a Markov inequality. Okay, so what does this mean? This means that if we sum over all s least twice the influence of f, s squared, then this is at most a half. Okay, if you don't like this Markov, then you can do it directly, but it's the same thing. Okay, and this implies that if you sum over all small s, I guess it's not to take most. And this is at least a half. Okay, because we assume that, well, yes, we don't necessarily assume anything, because the if you sum all of the Fourier coefficients, you get one. And we can also, because we assume that the function is balanced, then we can write it like this. Okay, so far we haven't done too much. Okay, and this is at most here. Sum over all I. Sum over all s containing I of size at most 2 in f of f at s squared. Okay, so maybe it's also clear why I would do such a thing. But what I'm saying is I'm adding here this thing, so it can only increase the sum. Okay, and then I'm decomposing it into all the i's in s. Okay, so this is like in the calculation of the total influence. Here stated differently, because I'm summing here over only non-empty S, then for each S I can find some index I which is contained in it. So this double sum will account for everything here. Okay, so it may be not so clear why I would do such a thing, but we'll see in a moment that this is a good idea. Okay, and this is sum over all I. IF minus 2 influence F squared. Okay, so let's write it IF and I needed to explain this notation for you. Okay, so we define G at most D. This is the low degree part of G. This is we sum over all S at most D, G hat over S, E S. Okay, so we take the Fourier expansion of the function. In this case, it's this LIF. And we throw out all the high degree terms. Okay, we only retain the terms that correspond to, in this case, it's at most, so this. We only retain the summand where the side of the set S or the degree of this the Fourier character is less than twice the influence of F. Okay, so it's still not clear why am I doing all of these things, but hopefully it will be clear in a moment. Okay, how did these people ever think of this proof? I don't know. But by now we have kind of an explanation of why it makes sense. So we'll see in a moment. Okay, so now we apply what's known as the level K inequality, weak level K inequality. Okay, so it states that for, so this is for 0 plus minus 1 values F, I think. Okay. G. Let's G at most D square is at most 3 to the D cube. So it should be a level D inequality, sorry. Okay, so what's going on here? So let's say the function is 0, 1. Okay, doesn't matter that it's could be minus 1. So if you look at the if you sum over all Fourier coefficients, then you should be getting the L2 norm of G. Okay. Now, let's say that the function G is very biased. Yeah, let's say it's mostly 0. Okay, then in this case, the L2 norm of G is small. So this thing is a lot smaller than the L2 norm of G. Okay, so this is the sum of all the Fourier coefficients of level at most D. And their sum is small. It's only like up to this factor, which looks scary maybe. But up to this factor, it's instead of the L2 norm squared, it's the L2 norm cubed. Okay, which is a lot smaller. So if this function in G is very biased, then most of its Fourier mass sits on high degrees. Okay, this is like we'll see in the proof that the reason that this is true is because low degree functions are tame. They're not too crazy. Okay, so if we take as a very extreme example a delta function, So a delta function, the mass is spread out evenly across all the levels. I will see in a moment. Okay, and it's very spiky, right? It's 0 almost everywhere, and it's 1 at a single point. Now, what this kind of says is that the only way for a function to be spiky is if it's a lot of its Fourier mass is on high degrees. Yeah, this is the best intuition I can give. Yeah, so let's see an example of this. So let's say that G is a delta function. So G of x is 1 plus x1 over 2 times 1 plus x2 over 2 times 1 plus xn over 2. Okay, so this is 1 if all of the xi are 1 and 0 otherwise. Okay, and if you write it as a Fourier expansion, then it looks like this. Okay, you just open this up, and this is what you get. This is how you compute the Fourier expansion. Okay, so if you compute g at most d squared, then you get n choose at most d over, I think, 4 to the n. Okay, and if you look at g over d squared over g squared, then you should be getting n to e over 2 to the n. Okay, so if d is not something like n over 2, then the mass up to level d is a very small fraction of the entire mass. So if you look at like the diagram of where the mass of this function sits, then it will look like a Gaussian, where this is n over 2. So if you look far to the left, then you will see almost nothing. So this function is extremely spiky, and for this reason, its mass is very spread across the different levels. And so the levels correspond to the size of the Fourier coefficient. And so the level D inequality is some quantitative way to state this. Okay, so again, if the function g is very biased, then this thing is a lot smaller than the L2 norm g squared. So this would mean that the mass beyond level D is almost everything. Okay, so there is some intuition here. I can't say that I understand it, but this is the intuition that people who do understand it convey. And let's see why this is helpful. So actually, we're almost done. Of course, up to proving this level D inequality. Yeah, let's also erase the example, so we have enough room. Yes, I'm sorry, a bit sorry if this is hard to follow, but the proofs are sometimes a bit mysterious. At least the proof is short. It can be worse. It can be like one of these proofs of Boolean, which are both long and mysterious. So that's even worse. This one is short. Okay, so we have the stopping f as it knows sum of I, L, I, F, most two imports of f. Let's say most 2c log n squared. And now we apply this level D inequality, or in the literature, sometimes it's called level K inequality. That's why I wrote K. So to be at most 3 to the 2c log n of I LIF Q. Yeah, I'm just copying what's written here. Okay, now this is the difficult part. The 3 to the 2c log n is the same as n to the, I think, 2c log 3. Then, and here's what we're going to do. So we're going to write it like this. Okay, so we're going to take out the maximal term of this form. Yeah, let's just write it. So is the sum of I LIF squared times the maximum over I of LIF. Okay, but what is this thing, this sum? So what is this thing?
No influence.
And this is the influence of coordinate I. So if you sum over all I, this is the total influence. This is influence of F. And this is square root of the ith influence of F. Okay, so we get 1/2 that promotes this n to the 2c log 3 times, so the influence is at most c log n times square root of the maximal influence. Okay, and if we square it, then we get that 1/4 is at most n to the 4c log 3 c squared log n squared times the maximal influence. Now I can choose c to be very small. Yeah, so maybe this thing is like at most, so we choose c so that this is at most n to the 0.1. If c is small enough, then this would be the case. And this would imply that the maximal influence the thing is something like 1 over n to the 0.1. So this 0.1 is arbitrary. It can be whatever we want. So this is about this optimizing the constant. So there's one place where it comes up. Okay, so if we choose c small enough, then we can force the maximal influence to be 1 over n to any power we want. And in particular, this is more than log n over n. Yeah, so what's happening here, roughly speaking? So what this calculation shows, so because the total influence is small, then most of the mass of the function is on small degrees. Okay, and in particular, this means that if you look at these LIFs, then also most of their mass in some sense is on the low degrees. So this means that these LIF functions, they can't be very biased, because otherwise most of their mass would be on high degrees. And if they're not very biased, then well, one of them has to be large. Okay, so this is like the qualitative story. So because so the fact that the total influence is small means that a lot of the mass of the function is concentrated on the low degrees. Yes, so again, the degree is the size of the Fourier coefficient, the size of S. Yeah, so because a lot of the mass is on the low degrees, then this is also the case when you look at these LIFs. Okay, and this means that these LIFs, they cannot all be very biased, because a biased function has most of its mass on high degrees. Okay, and if an LIF is not very biased, it means that it's well, the influence is large. The same thing. The influence is small, the function is very biased. Influence is large, the function is less biased. Yeah, so this is the sort of the story here. So you can't at one and the same time to keep all the mass downstairs, but for all the LIFs, for the mass to be upstairs. It just doesn't work out. Yeah, so there is a balancing act here. It can work out to some extent, and that's why you only get log n over m. Okay, so when you balance things, then you would get this log n over m. We don't see it from our calculation, but if you try to balance it, then you will get log n over m. Okay, so this is sort of the story. So either the Fourier mass is large, and then certainly one of the influences has to be large, or otherwise the influences, they can't all be small, because then this would imply that, well, that a lot of the math needs to be upstairs, and we kind of assume that this is not the case. Okay, so this is the best intuition I can convey. I think that the people who proved this, they didn't have this intuition, I think. So I was taught all these things by Ehud Friedgut. He has this Friedgut's Junta theorem, which is something very similar. And when he explained the proof, he just gave it step by step, and that was all. Okay, so you're getting a bonus. You're getting some intuition of non-Lifshitz. But this intuition is not necessary to prove this theorem. It's just necessary to understand the proof. Yes, I don't know if you have much experience in proving things without understanding what you're doing, but this is a nice example. Okay, the proof is kind of short, and you can follow all the steps, and they all make sense, but what's happening here? So I tried to tell a story, maybe it's convincing, maybe it's less convincing, but this is the best I can do. Yeah, so questions about this? Yeah.
Do you mean that the reason why we would get such a extremely better lower bound instead of this log n over n is because that we at the first step we assume that the function f is balanced.
No, so it's a question of choosing C. So we had two cases, and from case one we got log n over n.
Okay.
So that's what I said, like you don't see it here, but let's say that you don't know that the right answer is log n over n, and you try to optimize, then you would still get log n over n. If you balance what you get here with what you get here, then you would get log n over n. But you don't see it from this proof.
So I'm a bit confused by what you say about bias. What is bias?
Yeah, so the function f, we assume that it's unbiased. Okay, which means that it has the Fourier coefficient at the empty set is 0. And we used it here.
We give an upper bound on this.
Yeah, if you don't assume that it's biased, then what you need to do is you need to observe that when you sum all the non-empty Fourier coefficients squared, then you get the variance. And then this is the way that you sample things. So you only sample S subject to S being not empty set. And then you repeat the calculation and it still works out. So you can take it as an exercise. This is the only thing that you need to change.
And this upper bound, we bound one by S it seems to me is very loose. It's a very loose upper bound. But how could we get an optimal?
Yeah, so it's not that loose because it's only log n loose, sort of, because most of the mass is like at degree up to log n. But you're right, yeah, so there's some loss here. I guess that it's not a big deal. And maybe it would translate to some additive loss rather than multiplicative loss, I would guess. So we do know that this log n over n is the right answer up to constant. Yeah, but I mean, you're right that this proof seems lossy, and maybe you can squeeze a bit more out of it. But we don't care about constant factors, and that's why nobody bothered doing it. Sometimes they do care about these things, and for some other theorems like this FKN theorem or generalizations, we do know the best constant. But for the KKL, I'm not sure that this has been explored. But I think it makes sense. Like, even if you somehow you are able to test this conjecture that the Trimes function is optimal, or if you're able to improve over it, then it will be somewhat interesting. Yeah, so people really don't care about constant factors that much, but if let's say that it's true and you could prove that the Trimes function is strictly optimal, then I think they will care. Yeah, but you're right that the proof is a bit lossy, and this proof is very lossy because we got n to the 0.1. But you can optimize things, and if you want to really optimize things, then this level D inequality, this is a very bad level D inequality. You can actually get something a lot better. So you also need to do this, but we know I think the optimal level D inequality, so that has been done. Yeah, the one question which people do somewhat care about is about the degree D function, which I'll explain in a moment. So that's the one question where people do care about the exact answer to some extent. Okay, so more questions. And I'm sorry if this seems a bit unintuitive, but that's the way things are. Okay, so eventually the proof of this level D inequality is going to follow from hypercontractivity, which is something that we will probably get to tomorrow. But we will do it in steps. We can get to it today. Let's see. So yeah, this level D inequality, it follows from some property of low degree functions. Okay, so let's start by defining the degree of a function. And then I also give this question, which we, to some extent, care about the exact answer. Okay, so the degree of a function of f plus 1 to n with plus minus 1 is the maximal size of a non-zero Fourier coefficient. So it's the maximum set of S such that f hat of S is not zero. Forgot that. So this is denote the degree of f. If you think of the Fourier expansion as just writing f as a multilinear polynomial, so a polynomial where no variable is squared, then this is just the degree of the polynomial. Then we define the degree of the zero function to be 0. And now we can just take this question where people do care about. So there's a fact, Boolean function of degree D depends on order of the B coordinates. Okay, so if your function is Boolean and it's constant degree, then it depends on a constant number of coordinates. Yeah, but we don't know exactly how many coordinates it can depend on. Okay, so it's known that if it's degree 1, it depends on at most 1 coordinate. If it's degree 2, it depends on at most 4 coordinates, and this is types. If it's degree 3, then we also know the answer, but I don't remember, maybe 12 or something. But in general, we know that the optimal number is theta 2 to the d. So it's both order 2 to the d, and there's some construction which is some constant times 2 to the d. But we don't know the exact answer, and we even don't know the exact constant in front of 2 to the d. And people care about it to some extent. But this is one example where people do care about constants, at least a bit. Yeah, there are situations in Boolean function analysis where people really care about constants, but we won't see them here. This is like in majority of stablest, people do care about the constant. Okay, so this is just unrelated, and yes, open question. So find the exact maximal number of coordinates. So up to, I don't know, 5 or 10 years ago, then the best bound that was known was d times 2 to the d minus 1. But then it got improved to order 2 to the d. And then this improvement also got improved. Somebody improved the constant. So you can see that on this paper, they include together at least 4 authors who care about this question. So this is already something. Okay, so why am I mentioning this business with degrees? So, yes.
It's going to the that typing word problem.
I doubt it. But maybe we can discuss it. If it is, then it will be great. But we should discuss. Okay, so this level K inequality, level D inequality will follow from the following. I'm not to screw it up. Okay, so degree D functions are reasonable. So this is a general phenomenon. Okay, so h to the 4 and the most squared theory to the degree of h and h to 2, where HP is expected value of h to the p to the 1 over p. Okay, so this is LP norm. So in functional analysis, one defines these LP norms. Okay. These are the expectation of the absolute value of the function to the power p, and everything divided by raised to the power 1 over p. Okay, and this thing, it increases with p. Okay, so for this expectation measure, then it's monotone in p. When p is at least 1, between 1 and infinity, then these are actually norms. So they satisfy the triangular inequality. Yeah, so this is where the functional analysis comes in. Okay, so what's going on here? So this is L2 norm. So yeah, this means that we can compare the 4 norm and the 2 norm of a function if it has low degree. Okay, now in general, we cannot do this thing. So let's say that h is the delta function. H of x is delta 1 to the n x. Okay, so what is the P norm of h? So this is the expectation of h to the p to the power 1 over p. Now h is 1 on a single point. So this expectation is 1 over 2 to the n. So this thing is 1 over 2 to the n to the 1 over t. Now, so we get that h4, this is 1 over 2 to the n over 4. And h2 is 1 over 2 to the n over 2. Okay, and well, you can see that this is a lot larger than this. Okay, and in particular, if I take an arbitrary function h, I cannot bound the 4 norm of h in terms of the 2 norm. Unless I invoke n somewhere. Okay, so if I'm looking for an equality like this, where this thing is a constant, then I won't get it for arbitrary functions h. But what this means is that if h has low degree, then I am able to get such an inequality. Then this belongs to this genre of low degree functions are reasonable. Okay, so we said that the delta function, it has very high degree, it has degree n, right? Because the Fourier spectrum is full. So it's very spiky, and this is reflected in its degree, which is very large. Now, what happens is that if our function has low degree, then it's kind of not very spiky. Okay, so if you take it in the screen case, the 2 norm versus, let's say, the infinity norm is just the maximal value of the function. Then for a delta function, the infinity norm is 1, but the L2 norm is small. Okay, so this ratio between the norms kind of measures the spikiness of the function. So what this means is that low degree functions, they can't be too spiky. And for example, if you take a degree 1 function, then you can apply the central limit theorem, more or less with some asterisks. And you see that the function is kind of concentrated around its mean. Again, in particular, it's not very spiky. Okay, and this is kind of a quantitative way to state it for arbitrary degree. Okay, so we'll prove this tomorrow using hypercontractivity, which I will say what is tomorrow. So now we'll take this for granted, and we will prove this level the inequality. And you'll see the proof is quite short. Okay, so we want to bound on G at most D squared. So this is G at most D in a product with G at most D. But this is also in a product between G at most D and G. Okay, why is this the case? So if you apply Parseval identity, then this is, let's write it here. This is sum over all S of G at most D of S times D of S. But this is the same as sum over all S, G at most D of S squared. Because, well, if S is of size more than D, then this is just 0, so it doesn't matter.
Now you miss the height.
Right. Okay, and now we apply Helder's inequality here. Okay, so Helder's inequality is a generalization of the Cauchy-Schwarz inequality. Okay, so this thing works as long as 1 over 4 and 3 over 4 sum to 1. And now this thing is at most square root 3 to the d g over d 2. Okay, this is just applying this degree d functions are reasonable. And now if we divide with this, then we get that g at most d is at most square root 3 to the d times g to the 4/3. Okay, but I'm not interested in the 4/3 norm. I'm interested in the 2 norm. Okay, so we observe, let's take a new one. If you look at g to the 4/3 raised to the power 4/3, then this is the expected value of g to the 4/3. Okay, now this expected value of g, sorry, absolute value of g is either 0 or 1. So it doesn't matter to which power I raise it. Yeah, this is where we use the fact that this function is 0 plus minus 1 value. Okay, but something very similar will be true whenever the range of g will be, let's say, belong to some finite set. You can come up with a more general condition, but this will be enough. Anyway, in this case, this is just equal expected value of g squared, which is the L2 norm of g squared. Okay, so let's square everything. Okay, so if I haven't made a mistake, then we should be getting root to the d 2. Okay, so I've reduced one mysterious inequality to another mysterious inequality. So maybe it seems like I haven't made any progress, but this will follow directly from this hyperconductivity, whatever that is. Okay, and you can also see that the reason that this is true is because degree d functions are not spiky. Okay, and we use this trick, so this inequality. This is not in the original proofs. This is in these papers of Noam Lifshitz et al. So this is a trick to do this proof shorter way. Okay, so you can already see that there are some tricks involved, and there will be even more tricks tomorrow. The thing with these tricks, it's lacking combinatorics. Okay, so everything is a trick, but once you've seen 10 tricks, then you saw most of the tricks. Okay, so it's the same thing here. There is one big trick, which is hyperconductivity, which I'm going to explain tomorrow. And then there are maybe a few other things that you see here and there. And the hope is that once you've seen a few proofs, then you will be able to write your own proofs using similar tricks. Okay, this is just the way things are. And as you spend more time with it, then hopefully you gain some intuition. Yeah, some fields of math are like this, and some fields are worse. Analytic number theory is just a big calculation, basically, or algebraic geometry, where nobody understands what they're doing, and they can sometimes make mistakes and have no clue why or where. So here, at least, the proofs are usually somewhat short. The number of tricks is bounded. Yeah, so I think today was a bit maybe harder than yesterday. I think tomorrow will be better. Okay, so if you feel a bit lost, and then this hyperconductivity business, it's actually very elegant. Okay, so I encourage you to keep up the good spirits and also come tomorrow. So tomorrow the plan would be I will explain what hyperconductivity is. This will involve the noise operator, which is the missing character in the book. We will reduce this statement to hyperconductivity. This will be very easy. And then we will prove hyperconductivity, which is also very easy. It's just an induction. It's really a short proof. This is due to Alim Bonami. And afterwards, there will be some random blabber about around hyperconductivity, and then we will get to the topic of the final 2 weeks, which will be sharp thresholds. Okay, and this will involve the Fourier analysis over bias measures, over different measures, and we will see a version of KKL in that setting. So you will see a new proof of Bourgain's sharp threshold theorem. We won't see the entire proof because this will be too long, but we will see the interesting parts. And so that's for the rest of the week. Yeah, any questions?
I have a question.
Mhm.
Yeah, I'm kind of on the finance side.
Yeah.
Why we use a moment from the game, because we can use a increasing property of norm to bound the 4/3 to norm, and the
Yeah, but then you only get power 2. So it will be useless. You want to get a better power. But we will do this when we prove this Bourgain's theorem. So this will be good enough for us then, but not here.
I mean, for the inequality, why 4 and 2, but no.
Right, so actually, if you change the 4 and 2 to any 2 numbers which are, I guess, at least 2, and this one is larger than this one, then there will be a value of this one that will satisfy this inequality. Okay, we won't see it, but this follows from 4 to 2 hyperconductivity, where the noise rate is 1/√3. And you similarly have for any p larger than q at least 2, then you have a similar hyperconductivity with some constant, which we even have a formula for. So it's this is really square root of 4 minus 1 over 2 minus 1. So if you change the 4 and the 2 to something else, then you will get this similar inequality.
So we cannot do 3 to.
And you can do 3 too. So just change the 4 to a 3.
Oh, okay.
Well, sorry, I think I should have written before like this. Yeah, so this holds for any 2 nodes. I guess maybe I'm not remember if they have to be at least 2 or at least 1. But we won't see the proof because it's this calculation which is not very nice. Yeah, any more questions? So tomorrow we will see the proof of this thing using the hyperconductivity and prove hyperconductivity. So we'll see a complete proof of Technion.